Hey, welcome to Digital Signal Processing from Dr. Swapna T. Here today we will discuss the topic called the discrete time systems in frequency domain. What is a discrete system? The system which takes a discrete input and gives discrete output, we call it as a discrete system. Any discrete system is represented either using linear constant coefficient difference equation or by using its impulse response h of n. Okay, h of n is the impulse response of the discrete system. So for any LTI system which has the impulse response h of n can be represented in frequency domain. So the frequency domain representation of any discrete system is denoted by h of e to the power j omega, which is given as summation n equal to minus infinity to infinity h of n e to the power j omega n. This equation can also be derived using the Z transform equation. As we know, the h of z generally is given by h of z is equal to summation n equal to minus infinity to infinity h of n z to the power minus n. And we can substitute z equal to r e to the power j omega, r e to the power j omega, and for r equal to 1. And if I substitute r equal to 1, we will get this equation. So we can write h of e to the power j omega is equal to summation n equal to minus infinity to infinity h of n e to the power minus j omega n. This equation represents the frequency domain nature of a discrete system. Okay, so whenever we find the h of e to the power j omega, this is a complex in nature. So this h of e to the power j omega, it describes how the system scales and shifts the sensor input at any frequency omega. Thus, now if I am considering a system with input x and output y in frequency domain, let us say the input is x of e to the power j omega and output y of e to the power j omega. The relation between input and output in frequency domain can be given as y of e to the power j omega is equal to h of e to the power j omega dot x of e to the power j omega. It is similar to the convolution in time domain equal to multiplication frequency domain, because we know generally the in time domain the relation between x of n, y of n and h of n is y of n equal to x of n convolution with h of n. But when we are taking in frequency domain, it will become multiplication. So output in frequency domain will be equal to the multiplication of input in frequency domain and the impulse response in frequency domain. Thus, directly we can say using applying convolution, we can have y of e to the power j omega is h of e to the power j omega into x of e to the power j omega. Now, it exhibits some properties. The frequency response of any discrete system has some properties. That is, first, as we know that h of e to the power j omega will be complex in nature, so it will have some amplitude, some real term and some imaginary term. So depending on that, we can have the magnitude. So mod of h of e to the power j omega represents the magnitude response, and angle of h of e to the power j omega represents the phase response. Magnitude response shows how the system attenuates or amplifies at different frequencies, and phase response shows how the system shifts the phase of each frequency component. Coming to the stability of any system can be checked if summation n equal to minus infinity to infinity mod of h of n is less than infinity. That is, if the impulse response is finite, the system is stable. Similarly, causality, it is related to the region of the convergence of the Z transform. Okay, so here if I am considering any LTI system as shown in this block, h of e to the power j omega is the frequency response of the LTI system, which is a Fourier transform or Z transform of h of n. Let us say input in frequency domain given by x of e to the power j omega and output is y of e to the power j omega. So it has both magnitude response and phase response. So when I draw mod of h of e to the power j omega versus omega, we call it as a magnitude response, and phase, that is angle of h of e to the power j omega versus omega, will give phase response. So every system has its magnitude response and phase response. So this is the discrete time systems in frequency domain. So the system function can also be represented in Z transform, as I told previously. H of Z can be given as minus infinity to infinity, h of n z to the power minus n. As we know, Z equal to r e to the power j omega. If I consider r equal to unity, Z is equal to e to the power j omega. Thus, the practical uses of the system frequency responses, as we know, most of the every system can be one of this low pass, high pass, band pass, or band reject. So it helps in frequency design. So while designing these types of filters, these are defined with the help of equation h of e to the power j omega. So if we know the frequency response of the system, we can design that particular system. Similarly, we can have some applications in communication where OFDM systems generally rely on the frequency domain representation of the modulation and demodulation signal. Similarly, in spectral analysis, we can identify the spectrum, we can identify the noise, harmonics of useful signal components. So thus, the frequency response of any system is very important. Now we'll solve some example or one example on obtaining the frequency response of a discrete system. In this case, the discrete system is represented in the form of linear constant coefficient difference equation, which is given by y of n minus 2 y of n minus 1 plus 2 by 9 y of n minus 2 equal to x of n minus 3 by 5 x of n minus 1. Now we have to obtain the frequency response of this system. Now, as what is frequency response of the system? H of e to the power j omega. But we don't know h of n here, so we cannot directly take the Z transform of h of n. Instead, we have the linear constant coefficient difference equation, which is in the form of y of n and x of n. Now what you have to do, the first step is applying, you can write a Z transform, or directly you can take the Fourier transform on both sides. So if you take Fourier transform on both sides, let us say y of omega is Fourier transform of y of n, x of omega is Fourier transform of x of n. Okay, and the Z transform of y of n minus 1 will be e to the power minus j omega y of omega. It is by applying the shifting property, time shifting property. So we got y of omega minus 2 e to the power minus j omega y of omega plus 2 by 9 e to the power minus j2 omega y of omega equal to x of omega minus 3 by 5 e to the power minus j omega x of omega. Now simply we want h of omega. So we will take the ratio of y of omega by x of omega. So simply taking y of omega on left hand side common, x of omega on right hand side common, we can have the equation of h of omega. So this gives the h of omega, which is called as the frequency response of the system. If possible, you can solve for magnitude by separating real term and imaginary term, and you can have a phase also by taking minus tan inverse of imaginary by real. But up to this, we can directly obtain Z transform, and we can replace Z equal to e to the power j omega, or we can use a Fourier transform. By directly using the Fourier transform, we can obtain the frequency response of the system. Thank you for this.